All right, so what I'm going to do is today is I know that day 5 here, Coulombs Law, the start, was assigned for the other day when I was away, but I'm going to go over it again because it is the start of electric fields. Because again, this unit is primarily based on invisible fields, gravitational fields, or in this case, what we're going to look at is electric fields or electric forces that are created by those fields. And so what we have here is Coulomb's law. And so we have F of E, which is the electric force that is caused when two charged items, either positive, positive, negative, negative, or positive and negative, are around each other or even remotely around each other. And we can look at the forces that are exerted by each other on each other because of electric forces. Now, there's a lot of similarities between gravitational forces and electric forces. But the one main difference is that not only can you have attraction, you can have repulsion. And that is when we have charges that have the same sign, that is when charges repulse each other. Now, one of the key things that will come up in this formula, and we'll get to it, is that it is, the forces are directional, but you'll see in that formula that I have written up here for Coulomb's law, that there's no vector symbol on it, and it's because we have to determine the direction, because there is a possibility of both, like I said, attraction and repulsion of these charges. All right, so we'll get to, I'm going to go through a few examples here. I'm going to go past example 1, and again, I've adjusted the homework you'll see today on Google Classroom. I'm going to keep adjusting it as the day moves on, but I'm going to look at example 2 on my sheet. All right, dealing with Coulomb's law, and it asks, what is the magnitude of the force of repulsion between two small spheres that are 1 meter apart if each has a charge of 1.0 times 10 to the negative 12 coulombs? All right, so I'm just going to draw a little picture here. We have a charge here, and it has a charge of 1.0 times 10 to the negative 12 coulombs. And so does this one over here. They are matching forces. Now I'm going to call this one here A, and I'm going to call this charge here B. All right, now they are both positive. All right, because they have the same charge. Now, what I can do is I'm going to, and again, hold on here, I jumped the gun here. Distance between the two of them, 1 meter. All right, so now what I can do is that A puts a force on B and B puts a force on A. And because of that, the forces are actually going to be equal, but the directions will be different. And so, for instance, what I'm going to do is look at the force on A by B. All right, and that force, again, I'm going to use Coulomb's law here, where we have our K value, which is a constant, 8.99 times 10 to the power of 9, I believe. Don't have all these memorized. All right, and our two charges. We have a 1.0 times 10 to the negative 12, and we have a 1.0 times 10 to the negative 12. And of course, down below, I have a 1 squared. Nice and easy there. All right, well then, using my calculator, I can multiply, because our denominator is just going to be a 1, so it's not going to really matter at all. We're going to multiply the numerators here, and so if I do multiply those forces, I end up getting a magnitude of just 8.99 times 10 to the power of negative 50 newtons. Now, I'm not done yet, because this is the force on A by B. Well, what's B doing to A? Right, because it's the force on A by B. Again, I'm going to include direction here. Is that A, because they are both positive charges, they are repelling. And so the force on A by B is pushing A to the left. But again, because we're looking at the relationship between the two charges, I could also write this. The force on B by A Well, it's equal in magnitude and yet opposite in direction, because A is going to push B to the right. So again, because of the directionality or the fact that you can have both repulsion and attraction and its perspective, in one of these I'm looking at the force on A by B, or I can flip my perspective and look at the force on B by A. That is, you have to take that into account when you're determining the direction. All right, so let's try. We'll try number 3 here. Example 3. All right, so example 3, similar, but yet different. All right, so example 3, a small sphere carrying a charge of -8 microcoulombs. So we'll get into that. It's got a little funny symbol there. Exerts an attractive force of 0.5 newtons on another sphere carrying a charge of magnitude 5.0 or 5.0 microcoulombs. Find the distance between the two spheres. All right, so again, there's our formula over there, Coulombs law. We have Q1. So one of our charges has a charge of -8 microcoulombs. All right, now what micro means is that's going to be -8 times 10 micro, -6. It's the opposite of million. Millions times 10 to the power of 6. This one's times 10 to the -6. All right, now the other charge is 5 microcoulombs. So I'm just going to write 5 times 10 to the -6 coulombs. Again, coulombs is a measurement of charge. And the force, Fe, is equal to 0.5 newtons. And of course, we're looking for the distance or the R value. Same thing. The distance away or the R value away. All right, so again, I'm going to substitute into my Coulombs law formula here. So I have 0.5. Now K is, again, 8.99 times 10 to the power of 9. Then we have, I'm going to run out of room here already. All right, 8. Now here's the thing with substituting this formula. Because the direction, the sign really doesn't mean anything to you in terms of the formula, but the sign does mean something to you in terms of whether they're attracting or repelling each other, which in the next example will become a little more clear. So it's not really important here. Well, you don't need to put the sign in. So I'm going to put an 8 times 10 to the -6. And we have a 5 times 10 to the -6. Running out of room here. All right. And we are trying to find R squared. All right. So the first thing I'm going to do is, and again, this is all about scientific notation, is I'm going to simplify the top. I'm going to do it piece by piece. I'm going to do it the long way. I won't do it all in one step. And so what I do, again, if you're struggling with scientific notation, is I multiply the numbers. So I'm going to take my 8.99, and I'm going to times it by 8, and I'm going to times it by 5. And I get this. I get 359.6. All right, times 10. So now I'm going to multiply the powers of 10 using my power rule. So I got 10 to the power of 9, and 10 to the power of -6, and 10 to the power of -6. And so when you're multiplying powers, you keep the base the same, which I've already done, and I add the exponents. So 9 plus -6 is a +3, plus a -6 is a -3. All right, over R squared. Now, this is something that we've had for all of you who just love that first unit with trigonometry. We had this quite a bit, but we're not doing trig, relax. We're just doing a number equaling a fraction. And the reason I have that is so that I can cross multiply. And so I have 0.5 times R squared is equal to, well, our number up there, 359.6 times 10 to the -3. All right, so then I just divide both sides by 0.5. And that'll give me r squared. So let's see here. Now what am I getting? I take that 3559.6 times 10 to the power of -3. Okay. Then I divide it by 0.5. And I get 0.7192. That's a lot of decimal places, but I'm just going to leave it in there because then when I take the square root of both sides to get rid of that number, I get a distance of 0.85 meters. Again, that's rounded to 2 decimal places. All right, so there's again just a little scientific notation work with for you. Now I'm moving on to example. What are we going to do here? Number 5. So we've looked at when 2 charges interact with each other, but that's not the case. You can have more than 2 charges. So we're going to look at when 3 charges interact and look what happens specifically to one of them. So let's get to example number 5. All right, so in example number 5, we have 3 charges, Q1, Q2, and Q3 are located on the diagram. So I'm going to draw the diagram here with the charges that are on there. All right, so let's see here. The little diagram, we get Q1, we got Q2, charge 2, and we got number 3 over here. All right. The distance here is 1.5 meters. All right, the distance here is 2.5. And it's obviously 4 all the way around. Now, Q1 here is -2 microcoulombs. Right, that's negative. Q2 here is -1.8 microcoulombs. And charge number 3 is 1.5 microcoulombs. All right, so I've got all the charges. And now what I want to do specifically is I wrote the numbers up here, but just to highlight what's really going on here, this charge is negative, this charge is negative, and this charge is positive. All right, so what we want to look at is, it says calculate the net force on Q3. Now, opposites attract, right? So when we look at negative Q1, Q2, hold on here one second. No, I want to make, the diagram's wrong here. I want to make Q2 positive and 3 negative. I want to change it up. So I'm going to have to change my symbols here. That's a better example. All right, so make number 3 negative and 2 positive. There we go. I want to change it up. All right, there we go. So there's our situation. So again, I'm going to make 1 negative, 2 positive, and 3 negative. There we go. Is that what it said anyways? Nope, I changed it. All right. Now, what we want to find out is the net force on number 3. So the first thing I'm going to have to do is I'm going to have to figure out 2 things. The force on 3 by charge 2. So I'm going to call that F32, I guess, F32. The force on 3 by 2. And I also have to calculate, I better give myself some room here, but the force on 3 by number 1. Those are the 2 charges that are acting on our number 3 here. All right, so let's go with the force on 3 by 2 first. Now, I've got my 2 charges, 1.8 microcoulombs and -1.5 microcoulombs. So I'm going to substitute into my Coulombs law. And so again, I got my K value, which is the 8.99 times 10 to the ninth. All right, now I got my two charges. I'm dealing with 3 and 2. All right, so I got my 1.8 microcoulombs, so that's 10 times 10 to the power of negative 6. 3 is going to be 1.5 times 10 to the negative 6. Now, I purposely left out the negative sign because, again, I have to determine the direction based on what's happening between charge 2 and charge 3. All right, so, and I got their distance here, which is 2.5. Is that meters or centimeters? No, it's meters. Good. I'll have to switch the units here. All right, so the force on 3 by 2. So again, I'm going to multiply my numbers here. And let's see here. So I go 8 point, little calculator work. And I end up with on the top, let's see here. So I got 8.99 times 1.8 times 1.5. All right, I get that. And then times 10. Okay, so on the top here, I've got 0.0242. All right, I'm just doing a little calculator work. 2.5 squared, 6.25. All right, so if I take those two numbers, and again, I'm going to put a little vector symbol on there because I am going to put some direction on it. All right, so I take my 0.02. I could have done this all in one step, but just to kind of break it down a little bit. And I get, I guess I'll go scientific notation here, 3.87 times 10, let's see, 1, 2, 3 to the negative 3. Newtons. Now, direction. The force on 3 by 2. Well, we have a negative symbol and a positive. So opposites attract. So number 3, the force on 3 by 2 is going to pull it to the left. All right, so that's what is happening to 3 because of 2. Now we go over here and we find the force on 3 by 1. So again, I'm going to substitute into Coulombs law. So I have 8.99 times 10 to the power of 9. There's my K value, the constant. Charge 3 is 1.5 times 10 to the negative 6 coulombs. And again, number 1, sorry, is 2 microcoulombs that we're going to put in. It's a negative 2, but again, we have to determine the direction and the distance. We have 1.5 meters and 2.5 meters, so put them together. That's going to be 4, and I got to square it. All right, so continuing on here. Well, I know on the bottom here, I'm going to have a 16, so that's 4 squared. Then I multiply out my other numbers here. And let's see here. So I go 8.99 times 1.5 times 2. And this time I get to 0.02697. All right. And I end up with the force on 3 by 1. Again, I'm going to put in scientific notation here. I get 1.68 times 10. Let's see here. 1, 2, 3, negative 3 again. Newtons. Now, what is the direction between 1 and 3? Well, they're both negative. So 1 is going to push, they're going to repel, and 1 is going to push 3 to the right. All right. So now we have the two forces acting on charge 3. And just like we did with Newton's laws and our second unit or third unit, we can find the net force by adding them up. And so F net, let's see here, right I always say is positive, so I'm going to have a 1.68 times 10 to the negative 3. Left I'm going to say is negative, so there's my big minus sign, 3.87 times 10 to the power of negative 3. I subtract those. And I'm going to put a big vector symbol on there because I'm going to be able to do that. And let's see here. I end up with negative. So this thing's going to be left 2 point. Let's see here. Going to be negative. Negative 2.19 times 10 to the negative 3. And like I said, when I typed it in, it was negative, which means net force is going to be headed left on this charge at this particular moment in time. So there we go. So that, again, that's a lot of forces that we did before, the type of thing about finding the net force, having one sign positive and negative. But again, finding their forces a little bit different because we're using Coulombs law here of looking at the forces between electric charges. And again, opposites attract, like ones repel. All right, so at 10 o'clock, we are going to extend this and basically find out, use Coulombs law a little more in depth.